You know when you're standing in the middle of some massive, open-plan, high-rise office, and you look down at the floor beneath your feet, and you just sort of wonder, what is actually keeping me from crashing straight through to the level below? We trust these structures with our lives every single day, yet we rarely ever think about the intense, invisible mathematics that guarantee our safety. Well, welcome to This Explainer. Today, we're taking a dense engineering calculation document and turning it into a thrilling obstacle course. We're going to put a mathematically modeled composite deck slab through an invisible gauntlet of brutal physical stressors, just to see if it truly has what it takes to survive in the real world. To figure this out, we're putting our slab through an absolute gauntlet today. We'll start with the anatomy of a slab, move into surviving one-way shear, see about resisting the punch, test bending under pressure, examine the deflection test, and finally deliver the final verdict. All of this math has to happen before a single drop of concrete is ever poured on a construction site. All right, let's kick things off with Section 1, Anatomy of a Slab. The raw materials. Okay, let's really dive into this. What you're looking at is the fundamental blueprint of a composite slab. Notice that dual-layer system? Up top, you've got a solid layer of structural concrete, and sitting right underneath it, acting as both the mold and a permanent structural partner, is the ribbed steel decking. These two totally different materials, they actually lock together to form one unified weight-bearing floor. To really understand this gauntlet, we've got to look at the baseline stats for our competitors. Our concrete, it packs a formidable compressive strength of 28 megapascals. The steel decking boasts a yield strength of 345 megapascals. Put them together, and you get an overall slab depth of exactly 120 millimeters. But the real numbers you want to watch are down at the bottom. These are the actual demands placed on this floor in a real building. We're talking a maximum internal shear force of 2 kilonewtons and a maximum bending moment of 2.4 kilonewton meters. So the big question today is, can these materials actually handle it? Let's find out. Moving into Section 2, Surviving One-Way Shear. This is the first test. Just as a quick refresher, one-way shear is this incredibly destructive internal force. It literally threatens to tear the concrete apart by forcing two adjacent sections to slide past each other in parallel, opposite directions. Imagine trying to forcefully slide two rough blocks of stone past each other. It's brutal. Now, what's really interesting about this is how the slab fights back. If you look closely at those darker, shaded triangle shapes sitting between the pitches of the steel deck, in this entire wide expanse of floor, it's only that specific shaded cross-section of concrete that is actively doing the heavy lifting to stop that shear force. The rest of it, it's kind of just along for the ride. We're talking about exactly 80,812.5 square millimeters doing all the work. So, does it survive? Oh, absolutely, in spectacular fashion. The required strength, meaning the absolute maximum shear force this floor is ever expected to face, is just 2 kilonewtons. But the actual calculated capacity of that tiny shaded concrete area, a massive 106.5 kilonewtons. That means the demand is a mere 1.9% of the slab's total capacity. So yeah, it crushes the first test without even breaking a sweat. But shear force isn't the only threat out there. Let's move to Section 3, Resisting the Punch. Concentrated loads. Picture this. You've got a heavy piece of industrial machinery, or maybe a super dense server rack resting on a really tiny footprint. In this scenario, we're dropping a 22 kilonewton load directly onto a localized surface area of just 100 millimeters by 100 millimeters. The slab can't just absorb this locally. It has to take that brutal, punching pressure and efficiently distribute it outward, like those curved lines you see there, spreading the stress to the surrounding materials. Otherwise, that pillar punches a hole straight through the floor. So, the crucial point here is comparing the punch to the shield. Our concentrated load is 22 kilonewtons. After crunching the complex geometry of how the steel and concrete distribute that force, the calculated punching shear resistance comes in at 25.9 kilonewtons. The slab safely catches the punch. It's operating at an 84.94% capacity ratio. Now that is a much closer fight than the first test, for sure, but it's still a definitive victory. Bruised but unbroken, our slab moves to Section 4, Bending Under Pressure. Flexural strength. Now, structural engineers absolutely have to predict exactly how a floor will fail before they ever approve a design. It sounds counterintuitive, but an under-reinforced slab is actually preferred because the steel stretches first, giving us a visible warning sag, meaning people have time to evacuate. But an over-reinforced slab, that threatens a sudden, catastrophic crushing of the concrete before the steel ever yields. There's zero warning. And well, when the engineers ran the numbers on our specific 120mm composite slab, the math classified it strictly as over-reinforced. Because the concrete here will fail before the steel even stretches, engineers can't rely on the safety net of stretched steel. They have to rely strictly on the floor's pristine, uncracked cross-section properties. So for our flexural capacity calculation, we have to use the massive uncracked moment of inertia value. That's 1.6 times 10 to the 7th power millimeters to the 4th, a huge number.
Armed with the correct formula for an over-reinforced slab, we face the test. The maximum bending moment expected on the floor is 2.4 kilonewton meters, but thanks to the insane rigidity of that uncracked section, the actual flexural capacity is an overwhelming 29.2 kilonewton meters. The required pressure is just 8% of the total capacity. Honestly, our slab defeats the bending pressure with flying colors.
All right, we're almost there. Section 5, the deflection test. The final hurdle. Now we shift from catastrophic failure to human comfort. We need to stop the floor from visibly sagging under everyday use. Let's move to a case 2 double-span condition to see how this builds out. Imagine a continuous floor stretching across 3 support beams, which gives us 2 2300mm spans. Across this whole setup, we're applying a standard heavy real-world load of 10 kilonewtons per meter. This simulates everything from heavy desks to walking people. And this brilliantly illustrates the results of our human comfort test. Building codes dictate that for a span this size, the absolute maximum allowable sag is 9.58 millimeters. Anything more than that, and you'd literally feel the floor bounce under you. Talk about anxiety, right? But under that heavy 10 kilonewton load, our composite slab's actual deflection is a microscopic 0.614 millimeters. We're talking a fraction of a single millimeter here. It is completely, totally unnoticeable to human senses.
The dust has finally settled. It's time for Section 6, the final verdict. Safe to pour. Let's run through this checklist of victories, shall we? One-way shear. It vastly exceeded the required capacity using less than 2% of its strength. Punching shear. It successfully absorbed the 22 kilonewton concentrated load of heavy machinery perfectly safely. Flexural strength. Even as an over-reinforced slab, it utterly defeated the required bending pressure. And finally, deflection. The everyday sag is less than a millimeter, making it completely unnoticeable. The numbers are crystal clear and the math is absolute. This composite slab has conquered the invisible gauntlet and is officially certified as safe to pour. You know, engineering isn't just about mixing concrete and steel. It is about relentlessly anticipating every conceivable way the universe might try to tear a structure down and defeating those forces on paper long before the ground is ever broken. So next time you stand on a high-rise floor enjoying the view, take a moment to look down and ask yourself, how many invisible gauntlets did this floor survive before you ever took a single step? Thanks for joining me on this explainer to explore the fascinating hidden math beneath our feet. Keep observing, keep questioning, and keep learning.